Okay, question 14 now on this paper 1, and what we've got here is a forming and solving a differential equation question. Okay, so let's have a look and see what it says. A balloon, again, quite a popular idea, so I'm sure I've seen these balloons more than once. A balloon is being inflated. In a simple model, the balloon is modeled as a sphere. The rate of increase of the radius of the balloon is inversely proportional to the square root of the radius of the balloon. At time t seconds, the radius of the balloon is r centimeters. Write down a differential equation to model the situation, 1 mark. Okay, so what we've got is it tells us the rate of increase of the radius. So that is dr by dt. That's the rate of increase of the radius. So dr by dt is inversely proportional to the square root of the radius. So dr by dt is proportional to 1 over the square root of the radius. Now, the balloon is being inflated, the question tells us. So therefore, dr by dt is going to be plus positive k over root r. Okay. I think there has been a previous version of this kind of question where it was a mint was in somebody's mouth and the mint was being sucked. So therefore we had a negative in that kind of situation, okay? But in this one, the balloon is being inflated. So we've got a positive value of k. So we've formed that's part A done there for the 1 mark. This is a differential equation. So what a differential equation is one that has a derivative, like in this case, dr by dt in it. Okay, so part B now. It says, at the instant when t equals 10, the radius is equal to 16, and the radius is increasing at a rate of 0.9 centimeters per second. Solve the differential equation to show that that equation is true. So in order to solve a differential equation, the technique we use is something called separating the variables. Okay, and the way that separating the variables works is we imagine that this is a fraction. And we try and get everything that has an r over one side and everything else over the other. So we imagine that we're multiplying by this root r. Okay, so the integral of root r dr is equal to the integral of k dt. Okay, so therefore we're now going to integrate. So we raise the power by 1 and divide by the new power. So root r goes to r to the 3 over 2 divided by 3 over 2. And then we have k is going to go to kt add c. Okay, so we've now integrated. And r to the 3 over 2 divided by 3 over 2 can be thought of as 2/3. Okay, so that's going to be 2/3 r to 3 over 2 is equal to kt add c. So we're now just going to sub in our t is equal to 10 and our r is equal to 16. So in order to we've got to find out what k is and find out what c is. So the question tells us that when t is 10, that the radius is 16. So I'm just going to, this by the way has a special name. This is called our general solution, GS, the general solution. And that's the name of the equation when you don't know what the constants are. So we're going to try and solve this. Further mathematicians know all about this. We're going to try and find now the constants. So we're going to sub in our boundary conditions of t is equal to 10 and r is equal to 16. So that gives us 2/3 is equal to r is 16 and t is 10. So you work that out and you end up with this equation, which has got 2 unknowns in. So now when they give us 2 pieces of information, then that means that that's going to help us find out what both of the unknowns are. So if you have 2 unknowns like k and c, you're typically going to be given 2 pieces of information, 2 boundary conditions. And the second boundary condition that we've been given is that when t is 10, that dr by dt is equal to 0.9. Okay, so we can sub that in to find an expression for k. So we found before that our differential equation was that dr by dt is equal to k over root r. So we can sub in dr by dt is 0.9. So we have 0.9 is equal to k over root r. R is equal to 16. So that gives us k is equal to 3.6. So now we know that k is 3.6. We can come back to the equation that we just found a moment ago when we subbed in our 10 and R16, we got to this expression here. So we're going to sub in now the k into there. Okay, so there's the expression from just a moment ago. And we're going to sub in the k is 3.6 into there now. So when we do that, that gives us that c is 20 over 3. So we've got this equation here. Okay, and it's looking really close to what we're after. The only thing that's different is we've got 2/3 r to 3 over 2, but the question wants us just to have r. So we're going to times everything by 3 over 2, okay, to get rid of this 2/3. So when we times everything by 3 over 2 to help us get rid of the 2/3, lo and behold, we get the solution. And this is something called the particular solution. So if I write PS to stand for particular solution, you don't need to write that down. I'm just writing that down for interest. So the radius is equal to 5.4t plus 10 as the question is, as we're trying to prove. So that's 6 marks done. We're 6 marks in. There's just 3 marks left, so 2 little bits left now. Part C, it says, hence find the radius of the balloon when t is equal to 20. So we just sub in t is equal to 20. So that gives us, we've got 20 going into our equation now. In fact, the good thing about this one is even if you didn't do part B, you can still pick this up and get the marks from part C and part D. It's kind of nice the way they've kind of put a break point, as it were, into this. So yeah, we now kind of sub in the t is 20, work that out, that gives you 118. We want to make r the subject, so we put both sides to the power of 2 over 3. Because when you do that, you get that 3 over 2 times 2 over 3 is 1. So that means that the radius is 24.058. The question says give it correct to the nearest millimeter. So that's going to be to the nearest millimeter. We're going to have that's going to be 1. Okay, there. So it's going to be 24.1 if we give the answer correct to the nearest millimeter. Okay, suggest a limitation of our model. Well, the model that we've got, it suggests that let's go back to the equation. If I just find the piece of paper I've just thrown on the floor. Yeah, here's our model, okay, there. So what this model suggests is that as time increases, the radius is just going to increase and increase and increase. So which is not really very realistic. So this model predicts the infinite growth of the radius. And that's not realistic because the balloon is probably in real life going to burst when it gets beyond a certain point. Okay, so that's our limitation of the model. Perfect. I hope you found that helpful, and I will see you in